In module 6 of chapter 9, we shall deal with various examples where we shall find the different types of curvatures on the surfaces. The Gaussian curvatures, normal curvatures, principal curvatures, lines of curvatures, all these things we have learned about in our previous modules. So, here we shall take some examples and we will try to find all these things on that surfaces. Specially, we treat the right helicoid, that means we shall consider a right helicoid, and there we find all types of things, that is principal curvatures, normal curvatures, lines of curvatures, all these things we shall try to find for the surface right helicoid. So, let us start to find all these curvatures for different surfaces. So, here in module 6 of chapter 9, we shall deal with some problems on surface embedded in space. Let us see the first problem. So, here we shall find the Gaussian curvature at the point 2, 0, 1 for the surface given by the equation x square minus y square equal to 4 z, where x, y, z are rectangular Cartesian coordinate system. So, this equation is given in Cartesian coordinate system. We try to find the Gaussian curvature for this surface. This is a hyperbolic paraboloid. So, for this surface we are trying to find the Gaussian curvature. Now, if we convert this one into parametric equation, then we write x equals to u plus v, y equals to u minus v, and z equals to u v. And at 2, 0, 1, we have u equals to 1, v equals to 1. So, for curvilinear coordinate, we have u equals to 1, v equals to 1. So, the coefficients of the first fundamental form we can find by this way: a11 equals to del x del u square plus del y del u square plus del z del u square, and if we just calculate these things, we get 2 plus v square. So, similarly, as we have obtained this a11 which is coming to 2 plus v square, a12 which is equal to a21 is equal to u v, and a22 will come to equals to 2 plus u square. So, we have obtained the three coefficients a11, a12 and a22. So, we can find the determinant of that a alpha beta, that is the value of a, which is equal to the determinant of a11, a12, a21, a22, and if we put the values, we get a equals to 2 u square plus v square plus 2. Again, Ru, that is the partial derivative of r with respect to u, is coming to 1 v, and Rv, that is the partial derivative of r with respect to v, is coming to 1 minus 1 u. So, we can find the xi, which is the surface normal, and that can be obtained by this expression Ru cross Rv by mod Ru cross Rv, because xi is a unit surface normal vector, and which is coming to this one 1 by root over 2 u square plus v square plus 2 in the bracket u plus v comma v minus u comma minus 2. Now, if I find xi u and then take the inner product or dot product with Ru, we get B11, and if we perform this one, you can easily calculate this one, that B11 is coming to 0. B12 from the definition of the coefficient of second fundamental form, B12 is equals to minus half xi u dot Rv plus Ru dot xi v, and that will come to minus 2 by root over 2 u square plus v square plus 2. And similarly, we can find B22, that is the dot product of Rv and xi v, and that will also come to 0. Anyone can calculate this one by taking the partial derivative of xi with respect to v and then performing the dot product with Rv. B22 will come 0. So, determinant of B alpha beta, that is the B, is coming to this value minus 2 by u square plus v square plus 2. So, we have obtained the two determinants. One is A, that is the determinant of the coefficients of first fundamental form, and we have also obtained the value of B, that is the determinant of the coefficients of the second fundamental form, which are obtained in this way. Therefore, the Gaussian curvature is k equals to B by A. We know from the Gauss equation, this is the Gaussian curvature, which comes to minus 1 by u square plus v square plus 2 whole square, and at the point u equals to 1 and v equals to 1, the Gaussian curvature is coming to minus 1 by 16, which is less than 0. So, we can say that the hyperbolic paraboloid, that means this surface, is a surface of negative curvature. Now, we consider another example, that is the surface of right helicoid, and we will show that the right helicoid is a minimal surface, and also we shall find its normal curvature and Gaussian curvature. The parametric equation for the right helicoid is x1 equal to u cos v, x2 equal to u sin v, x3 equal to c v, where c is a constant. Therefore, A11 equals to 1, A12 equals to 0 and A22 equals to u square plus c square. We can easily find this coefficients of the first fundamental forms, that A11, A12 and A22. And so, A the determinant of A alpha beta is equal to u square plus c square, and A upper 1 1, that means the reciprocal tensor of A 1 1 is 1, the reciprocal tensor of A 1 2, that is upper A 1 2 equals to 0, and reciprocal tensor of A 2 2, that is A upper 2 2 equals to 1 by u square plus c square. Now, also we can find R u, the partial derivative of r with respect to u, and R v, partial derivative of r with respect to v. From here we can also find the value of xi, because we know that xi equals to R u cross R v by mod of R u cross R v. So, R u cross R v, we have obtained this one, c sin v minus c cos v comma u, and xi is this one, c sin v by root over u square plus c square minus c cos v by root over u square plus c square, and u by root over u square plus c square. So, this is the unit surface normal vector for the right helicoid. So, B 1 1 is the dot product of R u and xi u. So, if you find the value of xi u and xi v from the above expression, and if we take the dot product of R u and xi u, we are getting B 1 1 equals to 0. You can easily calculate these things. B 1 2 is equal to minus c by root over c square plus u square, which is equal to B 2 1, and B 2 2 is also equal to 0. Thus, H, which is the mean curvature, and by definition it is half A upper alpha beta B alpha beta, and if we just express this one as A 1 1 B 1 1 plus A 1 2 B 1 2 plus A 2 1 B 2 1 plus A 2 2 B 2 2, and if we put the values obtained earlier in this expression, we are getting H equals to 0. That means the mean curvature is 0, and so it is a minimal surface. So, right helicoid is a minimal surface. Now, the Gaussian curvature is equal to B by A, which is coming to minus c square by u square plus c square whole square, which is also again less than 0. So, the right helicoid is also a surface of negative curvature, and also the kappa n, we know that the normal curvature of a surface kappa n is equal to B by A, where B is the second fundamental form and A is the first fundamental form, and B is actually B alpha beta du alpha du beta, and A is A alpha beta du alpha du beta, and the expression is coming like this, minus 1 by root over u square plus c square, and in the denominator we are getting du square plus u square plus c square dv square, and in the numerator it is coming 2c du dv. So, this is the expression for normal curvature. Now, here in this example, we shall try to find a condition for the surface right helicoid to be minimal in terms of principal curvatures. So, let us see, we have seen that the right helicoid is a minimal surface because its mean curvature is 0. Now, what will be the expression in terms of principal curvatures? Let us see in this problem. Just from the previous example, we know this one, x1 equals to u cos v, x2 equal to u sin v, x3 equal to cv, the equation for right helicoid, a11, a12, a22 in a similar manner what we have obtained, a upper 11, a12, a upper a22, and also we have obtained b11 equals to 0, b12 equals to minus c by root over c square plus u square, and b22 equals to 0. So, all are required to find the principal curvatures, and b is this one. Now, the equation for the principal curvatures is, we know this one, kappa square minus a alpha beta b alpha beta kappa p plus b by a equals to 0. This is the equation for the principal curvatures we have seen earlier in our previous modules. Now, for right helicoid we have h equals to 0, and so kappa p square minus, so the middle term is equal to 0 and the last term is coming to minus c square by u square plus c square whole square equal to 0. So, kappa p equals to plus minus c by u square plus c square. So, these are the principal curvatures we are getting. So, kappa 1 equals to c by u square plus c square, and kappa 2 equals to minus c by u square plus c square. So, these are the two principal curvatures for the surface of right helicoid. Now, from that quadratic equation, since the sum of the roots equals to, we know that this 2h. So, kappa 1 plus kappa 2 equals to 2h, and we have h equals to 0. Therefore, the condition for the surface right helicoid to be a minimal surface in terms of principal curvatures is kappa 1 plus kappa 2 equals to 0. So, this is the condition for the surface right helicoid to be a minimal surface in terms of principal curvatures. So, in the previous examples we have seen the nature of Gaussian curvature of a hyperbolic paraboloid, and also we have obtained the normal curvatures, the Gaussian curvature, and the principal curvatures of a right helicoid, and we have obtained the condition for the right helicoid to be a minimal surface in terms of principal curvatures. Now, next we shall try to find the equation of lines of curvature for the right helicoid with some other one or two problems. So, now in this example we shall try to find the equation for the lines of curvature for the surface right helicoid. Now, just before we have obtained these values, again for equation x1 equal to u cos v, x2 equal to u sin v, x3 equal to cv, we have a11 equals to 1, a12 equals to 0, a22 equals to u square plus c square, and the coefficients of the second fundamental form, that is B11 equal to 0, B12 equals to minus c by root over c square plus u square, and B22 equals to 0. So, with the help of these values, we can find the equation for the lines of curvature. If we put these values in this equation, B11 A12 minus A11 B12 du square plus B11 A22 minus A11 B22 du dv plus B12 A22 minus A12 B22 dv square equal to 0. So, we know that this is the equation for the lines of curvature, and if we put all these values in this equation, we get this expression minus A11 B12 du square plus B12 A22 dv square equal to 0. Now, putting the values of A11, B12, B12, A22, we get this expression c by root over c u square plus c square du square minus c by root over u square plus c square u square plus c square dv square equal to 0. So, from this equation we get this equation du by root over u square plus c square equals to plus minus dv. Now, integrating both sides, we get v equals to plus minus sine hyperbolic inverse u by c plus d, but d is integrating constant. So, these two equations are the equations of lines of curvature for the surface of right helicoid. Now, this is an example where we have seen that the inner product of A upper alpha beta, that means the reciprocal tensor of A alpha beta, the first fundamental form, and C alpha beta is nothing but equals to 4 h square minus 2 k. So, A alpha beta, C alpha beta is equal to 4 h square minus 2 k. We shall prove this one. Now, from the proof of relations between first, second and third fundamental forms, we have k A alpha beta equals to 2 h B alpha beta minus C alpha beta. This expression we have obtained in module 1 of chapter 9. So, from this expression we get, just transforming the equation in this form, C alpha beta equals to 2 h B alpha beta minus k A alpha beta. Now, taking inner product with A alpha, A upper alpha beta, that is the reciprocal tensor of A alpha beta, in both sides we have A alpha beta C alpha beta equals to twice h A alpha beta B alpha beta minus k A alpha beta A alpha beta. Now, we know that the mean curvature is equal to 1 by 2 A upper alpha beta B alpha beta, and A upper alpha beta A alpha beta is equal to 2. So, if we calculate this one and if we put the values in the upper equation, we get A alpha beta C alpha beta equals to 4 h square minus 2 k. So, this is the relation obtained between the product, inner product of A alpha beta C alpha beta with the mean curvature and Gaussian curvature. So, in module 6 of chapter 9, specially we have dealt with some problems on surface. That means, here we have obtained the Gaussian curvature, normal curvature, principal curvatures, lines of curvatures for different types of surfaces, mainly on right helicoid. We have given emphasis on right helicoid, because this is a very important surface, and we have obtained the condition for the right helicoid to be a minimal surface in terms of principal curvatures. We have obtained the lines of curvature, the equation of the lines of curvature in this module. So, with all these things we end this module.